What we're going to learn about today is how you deal with calculating the work done by a force if the force isn't constant. Okay, so in video 7.2, in the last video, and on the homework, we really focused on the fact that as long as your force is constant, there are 4 ways that you can calculate the work, right? So here's what we learned. We learned that you could calculate the work done by a force by multiplying the magnitude of the force times the magnitude of the displacement. I may have used d in the last video, but delta r is the same thing, times the cosine of the angle between those 2 vectors. Okay, so that was one way to do it. We also learned that if you wanted, you could either split your force or your displacement vector up into components, right? So we said, okay, well, we can multiply the force vector with signs times the component, why did it change colors again? Times the component of the displacement vector, which is parallel to the force. Okay, so that was one way to do it. Or, instead of splitting the displacement vector up into components, you could split the force up into components. So I can multiply the component of the force vector that's parallel to the displacement, multiply that by the displacement. Again, keeping track of signs. All right, or finally, you could use sort of the mathematical version equation for a dot product, which is you multiply the horizontal component of the force by the horizontal component of the displacement, and add that to the vertical component of the force multiplied by the vertical component of the displacement. All right, so those all worked, right? Oops. If f and theta are constant. Okay, it only works if your force and your angle are constant. But what if they're not? Okay, if your force is not constant, then you wouldn't be able to do any of these, right? Because your components and your forces would always be changing, right? So what we're going to do is what happens if the force is not constant, all right? Now, fortunately, what we're going to do, if the force is not constant, we're just going to focus on one dimension. So what that means is, if your force is this way, then your displacement will either be parallel or anti-parallel, okay? So that's one advantage, okay, is that if the force is not constant, we're only going to be dealing with either parallel or anti-parallel, all right? So in that instance, then, you can calculate your work by just multiplying your force vector by your displacement vector, keeping track of the signs, right? All right, so let's work through an example really quickly where the force is, in fact, constant, okay? So we're going to use gravity. All right, so our force of gravity is always negative mass times 9.8, okay? And so then if you wanted to figure out the work that gravity did, you would multiply that force of gravity times your vertical displacement, right? So if you move your object up, gravity's down, so your work's going to be negative. If your object is moving down, then your work will be positive, right? Because both your force and your displacement are working together. So let's do this. So suppose that I was to graph a function that showed the force of gravity as a function of position. And here on my notes, I wrote delta y. I think what I really want is y. I think that's going to make our life easier. Okay, so this is a little bit weird. Usually y goes on the vertical axis, right? But here, our force is depending on our position. So I'm going to put the vertical position on the horizontal axis, and then I'm going to measure my force as a function of that. So force of gravity. Oops. Force of gravity, right? Okay. So my position can be positive, or it can be negative. We're going to measure this in meters. And then my force of gravity is always just negative mg, right? So here's my graph. So no matter what the position is, that's my force, right? Okay, it's constant. Okay, so suppose I move my object from, say, a position of 1 up to a position of 4. Well, then the work would be my force of gravity times my change in position, right? So here my change in position is 3 times my force of gravity. Notice that's just this area, right? So this is my force of gravity, right? Negative mg. Okay. So the work, here's what we just figured out. The work is the area under the force graph. Okay. Now remember, when we say under in math class, that means the area between the function and the horizontal axis. Okay? All right, so here we had our force as a function of position. Now here it was y instead of x, but same idea. Okay? All right, now in math, anytime you see area, well, not anytime, but when you're dealing with functions and you think about area, that should steer you in the direction of thinking about integrals. Okay? So what I'm hypothesizing then is this. I think we can do this. I think what we are learning here is that to calculate the work done by a variable force, we're going to integrate the force with respect to position from our starting position to our ending position. Okay? So if you're given the graph, you find the area. If you're given the function, you're going to integrate the function. All right? So let's think about a spring, okay? Because a spring is a non-constant force, right? Remember, the more you stretch the spring, the more force it exerts, right? So what we learned was the force of a spring, on this sheet here I've called it Fe as an elastic force. We learned that's negative K times X, where K is your spring constant, right? All right, so now I can't just multiply. All right, so let's make another graph. So what I'm going to do is, once again, I'm going to put my elastic force on the vertical axis. I'm going to put how much we stretch the spring on the horizontal axis. And if I graph that, it's going to give me, if I graph this, it's just going to give me a nice straight line with a slope of K, right? Okay, oops, upside down, isn't it? Sorry. It's going to go down. Okay. So suppose I want to figure out how much work the spring does from 0 to some final position. Okay? All right, well, based on what we just learned, it should just be this area, right? Okay, so what would that area be? So let's see. So this is a triangle, so my base is just going to be x. Now, if f is negative kx, then that means this, oops, oh, come on, stupid computer. So that means this is going to be negative k times x, right? So this area here is, let's see, 1/2 times base times height, which gives me negative 1/2 kx squared. Oh, and look, 1/2 kx squared, that's the equation for elastic potential energy, right? Okay, so we'll learn later on when we get to, I guess it'll be unit 9, we'll learn why that negative is there. But notice there's a connection there, right? The force, the work done by the force, remember, work is a change in energy, and here's the energy our spring has, right? Kx squared, 1/2 kx squared. All right, now suppose we did this mathematically. All right, what we just learned is that work is the integral of the force with respect to position. So the work done by our elastic force should be the integral of our elastic force with respect to position from a starting position of 0 to an ending position of x. All right? Somewhere there's a math teacher that's really mad at me that I used x twice here. That's kind of bad form, but I'm going to ask you to forgive me. Oops. Erase. Boop. Boop. Oh my goodness. Okay, so what is this integral then? Well, that integral is the integral from 0 to x of negative kx dx. Okay, well, what's the integral here? Well, the integral of negative kx is negative 1/2 kx squared, right? Evaluated between 0 and x, and it gives me negative 1/2 kx squared, which is the same thing we had up here. Hooray for physics. All right? So, here is what we've learned. To calculate the work done by a variable force, you can integrate the function like this, or if you're given the graph, instead of taking the integral, you find the area under the graph. Okay? All right, I just showed you the example of a spring. All right, now, so this works for any non-constant force. All right? So in this example, it says a net force is given by, it's 12 plus 1.4x. Okay, I don't know why I wrote it that way. So notice here, the force being exerted depends on the position. Thus, it is not a constant force. All right, so we're trying to find the work done. Well, the work done by a force should be the integral of the force with respect to position between my starting position and my ending position. So between let's try that again, between 0.5 and 2.5. So that's the integral of 12 plus 1.4x, evaluated at 0.5 and evaluated at 2.5, and then you just kind of grind out the math, all right? So this gives me 12x plus 0.7x squared, evaluated at 0.5 and 2.5. And so, I've got these written down over here. I'm going to trust that you guys can plug it in, right? So you're going to do 12 times 2.5 plus 0.7 times 2.5 squared minus 12 times 0.5 plus 0.7 times 0.5 squared. Subtract that, and you end up getting 28.2 joules worth of work. Okay? Now, keep in mind, I could have given you, instead of giving you this function, I could have given you the graph, right? I could have said, all right, suppose we've got a function, or suppose we've got, oh my goodness, suppose we've got a force that varies with position according to the equation, or according to the graph. You know, that as a function, that's going to look like this, right? 12, right? Okay, and so what you'd be doing then is you'd be figuring out, you know, what's the area between 0.5 and 2.5. So you'd be finding this area, okay? And that area would give you 28.2 joules, okay? Now, so let's do a graphy example, all right? So we've got a graph on the next slide. It says the graph here, shown here, represents a force being applied to a 2-kilogram cart as it moves along a track. Find the work done by the force as the cart moves from x equals 0 to blah, 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 blah. All right? And so here's the graph. All right? You might want to pause the video and draw this. Okay? So please be careful. This is where I see students make mistakes all the time. When we say the area under the curve, it does not mean this. I see students do this all the time. They find this area, and that's not what we want, okay? What we actually want is, so suppose we did the whole graph, okay? So what we would want is we would want this area and this area and this area and this area, and what color haven't I used yet? It's light green yet. Oops, light green. Oh my goodness, this thing. This area, and we haven't used red yet, and this area. Okay, so let's take a minute and do this. These are all either triangles or rectangles, right? So for this first one, let's do this purple area. All right, so this purple area is 1/2 base times height. So my base is 4, my height is 12. So 1/2, 4 times 12, that's the same as 2 times 12. So this is an area of 24 joules. All right, the yellow one is the exact same thing, but it's upside down, right? I've got a base of 4, a height of negative 12. So that's going to give me negative 24 joules. Okay. And so you just kind of keep going and you find all these areas, all right? So this area is going to be 3 times negative 12. Oops. 3 times negative 12, so that's negative 36 joules. This blue one here is 2 times negative 12, but it's half, so that's negative 12 joules. This green one over here is positive 12 joules, the red one over here is what, 3 times 12, so 36 joules. Okay? So to find the total amount of work done up to some point, you just add these, right? So I'm not going to go through all of them, but suppose we wanted to find the work done in the first 13 meters. So we're going from 0 to 13. Well, I would add up all of them up to 13, right? So that would be this one, so 24 plus this one plus this one plus this one. And so that gives you, what, negative 48 joules. All right? So there we go. So that's how you would find the work done if you're given a graph. All right? Now, sometimes, instead of giving you information about the force, I'll give you information about the work. Okay? So we'll go backwards, right? Because all of the ones that we've done so far, I've given you information about the force, either as a function or as a graph. Sometimes we'll go the other way. Okay? So, if we rearrange this, so what we started with in the last one was this. We started with the fact that in one dimension, your work was the force times the displacement, keeping track of the signs, right? Okay? But suppose I give you the work and ask you information about the force. Oh, well, then that gives you this equation, right? So in math, or in physics, I hope you guys are starting to realize that often when you multiply, we're talking about the area, right? Which should lead you to think about integrals. Often when we divide, that gives us information about the slope, right? And so that slope should lead you to think about derivatives, all right? So let's do this. Let's suppose I gave you, let's figure out what the graph of the work done by gravity would look like as a function of the vertical position. Okay? So here's my vertical position. Here's the work being done. Well, here's my equation, right? Work is force of gravity times my change in vertical position, right? Or times my vertical position. So my force of gravity is going to be negative mg. So this is negative mg times y. So here's what my graph is going to look like, right? And notice the slope of that thing is going to be negative mg. Okay? So what this is leading us to think is the slope of a work as a function of position graph is the force. Okay? Or the force is the slope of the work as a function of position graph. Okay? So let's kind of grind through another example here that's maybe a little bit more involved. All right? So let's see. So for a spring, here's our equation for the the elastic force, right? And we learned before that the work being done was this, right? So if I was to graph this, so here's my position, here's the work done by the elastic force. If I graph this, it's going to be a parabola that goes like this, right? And notice as you move along your x-axis, your slope starts at 0, and then it becomes more and more negative, right? Because as you pull your spring in a positive direction, the force gets more and more negative, right? Oh shoot, I was pointing the wrong way. But so if you pull it in a positive direction, the force gets more and more negative. Okay. All right. So this works for any kind of variable force. All right. So if I give you some variable force and I tell you that the work that it does is this, then I can find the force at any given spot, right? So here I've got this, I figured out that the work as a function of my position is this equation. So my force is just the derivative of that with respect to position. That's super important. This is dx, okay? We're going to learn later on that dw dt is power, all right? So it's really important that you think about, you can't just say the derivative of work is force. You have to say the derivative of work with respect to position is force. Okay? So this is the derivative of negative 4x squared minus 5x plus 7 with respect to position. So we're looking at negative 8x minus 5. So now I can figure out, for any given position, what my force is. Okay? I think that's it. I think that's all we need to do today. All right? Really quick summary. So here's basically what we've learned. If you are given, oops, let me use a different color here. If you are given a force versus position graph, then the area is the work done by that force. Okay? Mathematically speaking, that is this. The work is the integral of the force with respect to position between some starting position and some ending position. Okay? Now, if we flip it around, and I give you a work as a function of position graph, then the slope at a point gives the force at that point. Okay? So it's the slope of the tangent line, is what I probably should have said there. And so mathematically, that's this. Force is the derivative of work with respect to position. All right? So I guess what I should say is this. If you're given a graph, okay, there's no way that you could figure out this slope here, right, because it's a curvy function. So usually, if you're given a graph, a work versus position graph, it'll be a collection of straight lines. Okay? So, you know, the force at this point would just be the slope of this line. Okay? Alrighty. That is what I have for you today. How do I stop recording?